and take a look at 7.3. This is a longer lecture because there is a lot of material that we are covering in 7.3, so just bear with me as this video is going to be a little bit longer. In this video, we're going to be taking radicals with problems with multiple radicals in them and simplifying them into a single radical and then into a final answer. So we're going to learn a product rule, what to do when you're multiplying two roots, what to do when you're dividing two roots, simplifying them, combining like terms with them, the Pythagorean Theorem, the distance formula, and finally the equation of a circle. So 5, 6, and 7 objectives are basically us applying what we're learning in 1 through 4. So we're going to use the product rule for radicals. When you multiply two radicals with the same index, it's very important, it has to be the same. You can write them under one radical. You don't add anything, you don't subtract anything. You write them under one radical. So if I have the square root of 5 times the square root of 13, my index is the same, I can write them under one radical. Because 5 and 13 are both numbers, I can then multiply 5 and 13 to get the square root of 65. The square root of 65 is not a whole number, so I'm going to leave it alone. I can write it under one radical. Because 7, x, and y are different ones, I can leave it under one radical, but there's really nothing else I can do because I can't do 7 times x or 7 times y and get a simpler answer. Now in this one, part A, I have two cube roots. Write them under one radical. Complete the multiplication because these are both numbers. The cube root of 14 is not a whole number, so you leave it alone. In part C, it's the fifth root. They're both the fifth root. Write them under one radical. Oh, I'm skipping around. Part C, write them under one radical. Now what happened? Where did 72 come from? 72 came from 9 times 8. I'm skipping a step here, guys, to save us some slide space. Where does y to the fourth come from? It comes from y squared times y squared, means I add the exponents and I get 4. X squared comes from x times x, I add the exponents and I get 2. The same thing happens in B. I can write them under one radical, so I basically skipped this middleman step, and I did 8 times 2 is 16, r squared times r cubed, add the exponents, that's r to the fifth. In D, these are not like radicals. I can't do anything. That is the final answer, because my index is not the same. Now I'm going to look at the quotient rule for radicals. So instead of multiplying, I'm looking at division. When I have a fraction or division, remember a fraction is really just division, underneath a radical, I can break it up into two separate ones. It's almost like distributing the radical. What does this look like? Well, if I have the square root of 100 over 81, I can take that root and break it up into top and bottom. Now, I know what the square root of 100 is. I know what the square root of 81 is. They're whole numbers, so it's 10 over 9. Improper fractions are perfectly fine for my math lab final answers. You do not need to convert that to a mixed number. Same thing in B. I break it up as two separate roots. The square root of 11 is not a whole number. I'm going to leave that alone. Square root of 25 is 5. So you leave the 11 alone. You just don't mess with it. C, same thing. I'm going to break it up. I'm going to take the cube root. The cube root of 18 is not a whole number. You leave it alone. How did I know the cube root of 125 was 5? I probably did 1,000 problems, 1,000 practice problems, and it just stuck with me, or I entered it into my calculator. Some of these roots, guys, you're going to get really quick with as you go through this. In D, I'm going to break it up. Now remember, to simplify the y to the 8, I can do 8 divided by my index. Remember, the index is implied to be 2. 8 divided by 2 is 4. The square root of 16 is 4. So we're putting all of those rules from lesson 2 in play in lesson 3. Here I have a negative. The negative hangs out front. I write them as separate radicals. If I want to write this as a fractional exponent, it's going to be 2 divided by my index, which is 3. Not a whole number. I'm going to leave it alone. I'm going to do 12 divided by 3. That is a whole number. I'm going to go ahead and simplify that. That's as far as you need to take it. If this does not simplify to a whole number, feel free to leave it as a radical. Now we're just going to look at, okay, let's just simplify some radicals. Let's make things easier. Here are some conditions. The radicand has no factor raised to a power greater than or equal to the index. What does that mean? That means, like this case, there is nothing greater than 3 under my radical, so that's as simple as it gets. I don't need to simplify that. There are no fractions in the radicand, so I can't have the square root of 25 over 4. That's not fully simplified. I need to go ahead and break it out. No denominator contains a radical. This is very important for the lab. If you have a radical in the denominator, it's going to tell you it's wrong. Exponents in the radicand and the index of the radical have a greatest common factor of 1. That means that when I'm looking at the n value and the m value, they have no common factor, which means they don't divide evenly, like we just saw with x to the 2/3. There's nothing I can do, so I can leave that as a cube root of x squared. Here are some examples. The square root of 22, it's fully simplified. It's not a whole number. I leave it alone. The square root of 15xy, none of that square root's right. We're done. Cube root of 18, not a whole number. 3 is not bigger than 4. We leave it alone. These radicals are not fully simplified. What's the difference in the square root of 22 and the square root of 28? The difference is 28 has a factor that can be taken the square root. Okay, so I can factor 28 to where I can take a square root. That's the difference here. Then I can't have a fraction underneath root. I've got to make that the cube root of 3 over the cube root of 5, and then get rid of the 5 in the denominator. 7 over square root of 7. It is not fully simplified because it has a root in the denominator. The cube root of our 12 is not fully simplified because you can do 12 divided by 3, and that is a whole number. So let's look at simplifying these radicals. These are all square roots. So to know if a square root is fully simplified when there's just a number, you've got to figure out, is there any factor of 32 that is a perfect square? Factor meaning numbers you multiply together. 32 is 16 times 2. Now, if you're not great with times tables, just take 32, divide it by 4, divided by 25, divided by 16 to figure out if it has a factor. The square root of 16 is 4, so this becomes 4 times the square root of 2, because I can break it up. Same thing with 300. Is 300 divisible by a perfect square? Well, it's divisible by 25, but it's also divisible by 100, which is a perfect square. So I'm going to write it as 100 times 3. The square root of 100 is 10, so it's going to be 10 times 3. The square root of 35 cannot be simplified. It is not divisible by a perfect square. 54, the cube root of 54 is a little different. We're looking for perfect cubes. So 2 cubed is 8, 3 cubed is 27. Is 54 divisible by 8, divisible by 27? It's divisible by 27. I break it up into 2 cube roots. I know the cube root of 27 is 3. This is going to take some guess and check work in the calculator. The fourth root of 243, well, 2 to the fourth is 16. 3 to the fourth is whatever that value is. I'm going to keep checking. 3 to the fourth times 3 is 243, which gives me 3 times the fourth root of 3, because if I take 4 and 4 and divide them, I get an exponent of 1. Now I'm looking at, okay, is the number fully simplified? Is the exponent fully simplified? So the square root of 25p to the 7th. The index here is 2. 7 divided by 2 is not a whole number, so there's not a whole lot I can do just yet with that. But the 25, I can definitely take the square root of 25. Now, why did they break it into p to the 6? Because 7 divided by 2 is not a whole number. But if I break it up into p to the 6th times p, that is the same thing as p to the 7th. 6 divided by my index of 2 is a whole number. So I get 5 from the square root of 25. I get p to the third by doing 6 divided by 2 to get our rational exponent. Same thing in part B. Square root of 72, y cubed. I'm going to break y cubed up into y squared times y. So I get 6 squared, which is 36. So this is 36 times 2. I break the y squared. 2 divided by 2 is 1. And I can't take this y or this x any further because they don't divide evenly. 1 divided by 2 is not an even whole number. So we're going to keep building on this. Now we have the cube root of negative 27. So notice what we've done is we've taken all of these exponents and I've grouped them by even numbers because this is 3. 6 divided by 3 is a whole number. 3 divided by 3 is a whole number. 6 divided by 3 is a whole number. But these remaining x and y values would cause it to not be a whole number. So then I would do 6 divided by 3, which is 2. 3 divided by 3, which is 1. 6 divided by 3, which is 2. And then the cube root of 27, or negative 27, is negative 3. So this is a habit you have to get into for how to write these exponents out. Same thing in D. I'm going to write that as 2 to the 4th, or I could look for it being a factor of 2 to the 4th actually calculated out. A to the 4th times A, because I know I can do 4 divided by 4. B to the 4th times B cubed, because again, I know I can do 4 divided by 4. So that's where this answer is going to come from. There's nothing further you can do with this radical. We just leave that part alone. Now the 12th root of 2 cubed. Does it gain you anything to do this? Well, I can do this as 3 divided by 12, which is 1/4. And that does get me to the 4th root of 2. So just looking at this isn't enough to say, oh, that's not a whole number. You have to think about, am I going to get something I can reduce? So 3 over 12 reduces to 1/4. Same thing here. 2 divided by 6 is not a whole number, but I can reduce that fraction. When I reduce that fraction, I get 1/3, which means this can be reduced to the cube root of t. So think about, am I getting a whole number, or can I reduce the fraction? So this is another way of reducing things. If you have a factor like 6, 6 is 2 times 3. If this was 8, which is 2 times 4, the k values of 2 would cancel out. And I'd have 3 and 4. It's just a way of simplifying the radical. So now I'm looking at different indexes. So I have a square root times the cube root. That can be a little tricky. Since they have a least common index of 6, I can write each radical as a 6th root. It's kind of weird, right? So we know 5 to the 1/2 is the square root of 5. I can write this, if I have a common factor of 6, I want to make that denominator 6, so I have to multiply by 3 over 3. That's where this comes from. Same thing for 4. The common factor of 2 and 3 is 6. I'm going to multiply by 3 over 3 to get my 6, which gives this. Now that they're both in the same index, I can multiply them together to get the 6th root of 2,000. Why is this simpler? It's a lot of steps. It's simpler because it's under one radical. So this is like the common denominator situation with combining fractions. It's the same idea, but it's what you have to multiply by to go ahead and get that common index in the root. So all of this root information we've learned, what do we actually do with it? Well, we solve the Pythagorean Theorem. The Pythagorean Theorem says that a squared plus b squared equals c squared. I hate this formula. I use the one at the bottom. The leg squared plus the leg squared equals the hypotenuse squared. Hypotenuse is always across from your 90-degree angle. The legs are always the two that are touching the angle. So if I want to find the unknown side c, I first have to decide, is c a leg or is it a hypotenuse? Well, it's across from that right angle, so it'd be leg squared plus length squared equals hypotenuse squared. So I would have 14 squared plus 8 squared equals that hypotenuse value, which I see here. Then I'm going to take my calculator and I'm going to figure out what is 14 squared plus 8 squared. That's 260. 260 equals c squared. I need to get c alone, so I'm going to take the square root of both sides. If you are doing the Pythagorean Theorem and you are not taking a square root, you're doing something wrong. From there, I want to see, can I simplify the square root of 260? Is it divisible by a perfect square? It is. It's divisible by 4. If you didn't know that, just check, guess and check. 260 divided by 4, 260 divided by 25, 260 divided by 9, which gives me 2 square root of 65. If you entered the square root of 260 in the lab, it would be wrong. Here, I'm looking for b. B is a leg because it's touching the 90-degree angle. So I'm going to have 4 squared, which is a leg, plus b squared equals 6 squared. Now I need to solve that for b and get b alone. I'm going to go ahead and calculate my exponents out, and then I'm going to subtract 16 from both sides to simplify that and get the b squared. Now how do I solve for b with b squared? I take the square root. Is 20 divisible by a perfect square? Yes, it's divisible by 4. So it would be 2 square root of 5 for the final answer. The distance formula is going to be a little more complex than the Pythagorean theorem, but still completely doable. The distance formula is where we are plugging in x values and y values. The first point in the problem is x1, y1. The second point in the problem is x2, y2. Notice I subtract my x values, square them, and then add. The biggest problem is students subtract here. You add the y values subtracted and squared. So if I'm finding the distance between these 2 points, x1 is 2, y1 is -1. x2 is 5, y2 is 3. I'm going to plug into my distance formula. Now, this is where sometimes students make mistakes. I am perfectly okay with you typing 5 minus 2 in your calculator on a test to make sure you're getting that right, because we deal with negatives a lot in the distance formula. The same thing is true with 3 minus -1. You can type that into your calculator and you'll get 3 and 4. You square them, add them together, then take the square root. The square root should be the very last thing you do in any distance formula problem. Same question here. I'm doing a similar operation. x1 is -3, y1 is 2. x2 is 0, y2 is -4. I'm going to plug in the distance formula. Again, you can type 0 minus -3 in your calculator. -4 minus 2, you can type that in your calculator if you're not totally comfortable. Then you're going to square them, add them together, and 45 is divisible by 9, so it's 9 times 5, which reduces to 3, because the square root of 9 is 3. And the last thing is the equation of a circle. This is really another place where we deal with square roots. To find the equation of a circle, we have something called a center. And the center is a fixed point, and the circle is an equal distance from the center all the way around, 360 degrees. The radius of a circle is the distance from the center to the outside of the circle. We're going to use the distance formula to be able to find the radius. So I have an equation of a circle with a radius of 4 and a center at 0, 0. So I'm going to plot my center at 0, and 4 radius would be here, 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 and here, and then I will connect my dots. Now, what's over here with the distance formula is finding the equation. So I graphed the circle by putting dots on all those 4 ratios. But I can use the distance formula to find the equation of the circle. You plug in x1 and y1 for the center. So I plug that in, and that gives me x minus 0 squared plus y minus 0 squared. I square both sides. So square the square root, square the 4. That leaves me with x squared plus y squared equals 16 because minus 0 doesn't need to be written. This one has a center at 3, negative 2. So to find the equation, I'm going to use 3 for my x1, negative 2 for my y1. I'm going to simplify and I'm going to square both sides. The radius is always what you use for your distance, and you're always squaring both sides. Notice y plus 2. That's because minus a negative becomes plus a positive. Then you're going to put your point at 3, negative 2. You're going to put your circle and you're going to count 4 units over, put a dot, back to the center, 4 units up, put a dot, back to the center, 4 units this way, put a dot, back to the center, 4 units down, put a dot, and play connect the dots. So what I did was I did my here, I have it here, I have it here, and you just draw a circle through those points, okay? Doesn't have to be perfect. If I'm looking at an equation, I can find the center by what's being added or subtracted in the parentheses and then taking the square root of the radius. So if I want the equation of a circle at the center, 2, negative 1, my h is 2, my k is negative 1. My radius is square root of 10, so I'm going to take the square root of 10 and square it. So I have x minus 2, because that's my h, y minus negative 1, that's my k, and I square the radius. Minus a negative simplifies to plus, square root of 10 squared is 10. So this isn't the worst thing you can do. Sketching a circle in the lab can be a little tricky. It might help you to practice once or twice and then be able to move on to actually working the problem. And that is the end of 7.3. This is a long lecture. Feel free to pause as you need and go back over questions as you need.